Hello friends, welcome to 90 Plus My Tuition App. Friends, have you ever seen a mountain or a desert? Some of you must have, right? But not all of us. In that case, I will take you to these two places. Well, we all love the sight of ice mountains, right? So first let's visit a mountain. Wow, it is too cold here. But as the weather gets sunny, there happens a change. But what is that? Yes, this ice starts slowly melting into water. But what happens to this water in desert? Let's see. Look at me friends, I am sweating. It is too hot here. It is that much hot that the water here is evaporating into vapors. So friends, here we have visited two places, a mountain and a desert. So what do you have understood? Yes, water exists in three states, that is solid as ice, liquid as water and gas as vapors. Well, we know that atmosphere is made up of gases. However, solids are more common than liquids and gases. Really? Let's check out this by visiting a park. Wow, this is too beautiful, right? Well, this football, chair, seesaw, cycle, all these are solids. So now you know the importance of solids in our daily life. Then why don't we learn more about the solids? So in today's session, we are going to discuss chapter number 1, the solid state. So shall we start? Okay friends, now let's discuss the properties of solids. As we know, solids have a definite mass, shape and volume. In solids, the constant particles such as atoms, molecules or ions have fixed positions and they can oscillate about their mean positions. In solids, their intermolecular force is strong and intermolecular distance is short, and solids are incompressible and rigid. Now let's see the classification of solids. Based on the arrangement of the constituent particles, solids can be classified into two. They are crystalline solids and amorphous solids. Let's discuss them in detail. Crystalline solids have an orderly arrangement in their constituents such as ions or molecules in three dimensions. They are arranged in an orderly manner to give a definite geometry. Thus, we can say that crystal is a solid that has a definite geometrical shape. Then what about the properties of crystalline solids? Well, crystalline solids melt at a sharp and characteristic temperature and become liquid. When we cut them using sharp-edged tool, they split into two pieces and the newly generated surfaces are plain and smooth. Crystalline solids are anisotropic in nature. Anisotropic solids? What is that? If the magnitude of physical properties such as refractive index, thermal conductivity, electrical conductivity, etc. are different along with different directions of the solids, they are called anisotropic solids. Crystalline solids are the true solids. They have a long range of order. Quartz, diamonds, calcium fluoride, sodium chloride are some examples of crystalline solids. Now you must have understood about the crystalline solids. Now let's move on to the next solids, that is amorphous solids. The word amorphous has been derived from Greek word amorphos, which means shapeless. An amorphous solid consists of constituent particles that are arranged in an irregular manner. Thus, we can say that amorphous solids have no definite shape. Friends, what happens when you cut an amorphous solid using a sharp-edged tool? Well, it splits into two pieces with irregular surfaces. Amorphous solids are isotropic in nature. When the properties of material such as mechanical strength, refractive index and electrical conductivity are identical in all directions, then they are said to be isotropic material. Like liquids, amorphous solids have a tendency to flow at room temperature, and so they are called pseudo-solids or supercooled liquids. They have only short-range odors. Glass, plastics, rubbers are some examples of amorphous solids. Well, most of the solid substances are crystalline in nature. Metallic elements like iron, copper and silver, non-metallic elements like sulfur, phosphorus and iodine, compounds like sodium chloride, zinc sulfate and naphthalene are some examples of crystalline solids. Next, we will discuss the classification of crystalline solids. Crystalline solids are classified into two ways. On the basis of the nature of intermolecular forces or bonds that holds the constant particles together, crystalline solids are classified as van der Waals forces, ionic bonds, covalent bonds and metallic bonds. Crystalline solids are again classified into four. What are they? Let's see. Molecular solids, ionic solids, metallic solids, covalent or network solids. Let's discuss them in detail. So the first one is molecular solids. The constant particles of molecular solids are either atoms or molecules. They are held together by a weak force of attraction. Well, these molecular solids are further divided on the basis of their intermolecular force of attraction. Molecular solids are again classified into three. They are non-polar molecular solids, polar molecular solids and hydrogen bonded molecular solids. Let's discuss them in detail. So the first one is non-polar molecular solids. In non-polar molecular solids, the constituent particles are either atoms or molecules. In these solids, atoms are held together by a weak dispersion forces or London forces. As a result, these molecules have low melting points and so they are in liquid or gaseous state at room temperature and pressure. These solids are soft and non-conductors of electricity. Hydrogen, carbon dioxide, argon, carbon tetrachloride, iodine, chlorine are some examples of non-polar molecular solids. So the second one is polar molecular solids. In polar molecular solids, the constituent particles are formed by polar covalent bonds. In these solids, molecules are held together by relatively stronger dipole-dipole interactions. They are also soft and non-conductors of electricity. They have a high melting point as compared to non-polar molecular solids. They are also in liquid or gaseous state under room temperature and pressure. HCl, SO2, NH3 are some examples of these solids. So the third one is hydrogen bonded molecular solids. In hydrogen bonded molecular solids, the constant particles are molecules. And in these kind of solids, the intermolecular forces are strong hydrogen bonds. As a consequence, the molecules of these solids have high melting point among the three types of solids. Like other two solids, they are also non-conductors of electricity. They are volatile liquids or soft solids under room temperature and pressure. Ice, solid hydrofluoric acid are some examples of hydrogen bonded molecular solids. Now let's discuss the other type of crystalline solids, that is ionic solids. In ionic solids, the constant particles are ions. Here, the cations and anions are held together by a strong Coulombic or electrostatic force of attraction inside the crystal. Then what about their properties? Let's see. They have high melting points and they are hard and brittle in nature. But can they conduct electricity? Yes, in molten state or when dissolved in water, the ions become free to move and then they can conduct electricity. While in solid state, they behave as an insulator. Sodium chloride, zinc sulfide, magnesium oxide, calcium fluoride are some examples of ionic solids. Next, we are going to discuss about the metallic solids. In metallic solids, the positive ions are surrounded by mobile free electrons and are evenly spread all over the crystal. Each metal ion donates one or more electrons to the group of mobile electrons, which increases the electrical and thermal conductivity of the metallic element. Then what happens when we apply electric fields or heat to this metal? Let's see. When an electric field is applied, the free electrons inside the metal will flow through the network of positive ions. Similarly, when heat is applied to the one portion of the metal, the thermal energy is uniformly spread throughout by free electrons. The presence of free electrons in metals makes them lustrous, malleable and ductile. Chromium, copper, silver, magnesium and iron are some examples of metallic solids. Now let's discuss the last one, that is covalent or network solids. Here the constant particles in covalent solids are atoms. Atoms in large networks are held together by covalent bonds. So they are also called giant molecules. These solids are very hard and brittle in nature. They have extremely high melting point and they are also insulators and they do not conduct electricity. Diamond, silicon carbide are some typical examples of these solids. But graphite is an exception as it is soft and a good conductor of electricity. Friends, what makes graphite soft and a good conductor of electricity? Well, in graphite, each carbon atom covalently is bonded to 3 other carbon atoms in the same layer. The different layers can slide over the other. Here, the 4th valence electron of each atom is present between different layers and free to move. These free electrons makes graphite a good conductor of electricity. They are also soft and used as a lubricant. Well, the different types of solids and their properties are given in the table. Now you must have an idea about the classification of crystalline solids, right? Then next we will discuss about the crystal lattice and unit cell. Crystalline particles have a geometric arrangement of their constituent particles, and the position of the constituent particles in a crystal are shown by using points. These points are known as lattice points or lattice sites, and the arrangement of these infinite points are known as crystal lattice. It is called space lattice or lattice. Let's see other properties of crystal lattice. We have already discussed about the lattice points. These constituent particles may be atoms, molecules or ions. These lattice points are joined by straight lines to bring out the geometry of the lattice. Okay, now let's consider a small part of the lattice. The small part of the crystal lattice can be used to specify the crystal completely. This smallest portion of a crystal lattice is called a unit cell. Now let's discuss the parameters of a unit cell. In three-dimensional crystal system, a unit cell has 6 parameters. And these parameters are 3 edges and angles between them. As you can see, the dimensions along the edges of a unit cell are represented as A, B and C. These edges may or may not be mutually perpendicular to each other. The angles between the edges are represented using alpha, beta and gamma, where alpha is the angle between B and C and beta is the angle between A and C, and gamma is the angle between A and B. Friends, do you know these unit cells are broadly classified into two? They are primitive unit cell and centered unit cell. Let's discuss them in detail. So the first one is primitive unit cell. When the constant particles are present only on the corners of the unit cell, it is called primitive unit cell. And when the particles are present at the other position in addition to those at corners in a unit cell, it is called centered unit cell. Well, these centered unit cells are again classified into three. They are body-centered unit cell, face-centered unit cell, end-centered unit cell, or base-centered unit cell. So the first one is body-centered unit cell. Here, one constant particle lies at the center of the body of a unit cell in addition to the particles lies at the corners. Then what about the face-centered unit cell? Here, one constant particle lies at the center of each face besides the particles lies at the corner. So the last one is end-centered unit cell. Here, one constant particle lies at the center of any two opposite faces beside the particles lies at the corners. It can be concluded that based on lattice parameters, there are 7 popular crystal lattices. Do you know what are they? They are cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. Let's discuss them in detail. So the first one is cubic. In cubic, the possible lattices are primitive, body-centered and face-centered unit cell. Here, the edge lengths are of equal length. That is, A is equal to B is equal to C. And the three axial angles are of 90 degree. That is, alpha is equal to beta is equal to gamma is equal to 90 degree. Well, NaCl, copper, zinc blende are some well-known examples of cubic. So the second one is tetragonal crystal system. Here the possible lattices are primitive and body-centered. Here the three axial angles are of 90 degree. That is, alpha is equal to beta is equal to gamma is equal to 90 degree. And only two edge lengths A and B are equal. That is, A equal to B not equal to C. White tin, SnO2, CaSO4, TiO2 are some examples of these type of crystals. Moving to the third one, that is orthorhombic. In orthorhombic crystal system, their possible lattices are primitive, body-centered, face-centered and end-centered. In orthorhombic crystal system, the axial angles are of 90 degree. That is, alpha is equal to beta is equal to gamma is equal to 90 degree. And the three axes are unequal. That is, A not equal to B not equal to C. Well, rhombic sulfur, KNO3 and BaSO4 are some examples of orthorhombic crystal system. Moving to the next crystal system, that is hexagonal crystal system. The only possible lattice is primitive. Here, two axes are of equal length. That is, A equal to B not equal to C. And two angles are of 90 degree. And one angle is of 120 degree. That is, alpha is equal to beta is equal to 90 degree. And gamma is equal to 120 degree. Graphite, CDS, ZNO are some examples of hexagonal crystal system. Moving to the next crystal system, that is rhombohedral or trigonal crystal system. The only possible lattice is primitive. Here, three axes are of equal length. That is, A is equal to B is equal to C. As you can see, the only two angles are equal to 90 degree. That is, alpha is equal to beta is equal to gamma not equal to 90 degree. Calcite or calcium carbonate and mercuric sulfide or cinnabar are some examples of these type of crystals. Now let's discuss the second last one, that is monoclinic crystal system. Here the possible lattices are primitive and end-centered. As you can see, the three axes are unequal. That is A not equal to B not equal to C. And only two angles are equal to 90 degree. That is alpha equal to gamma equal to 90 degree and beta not equal to 90 degree. Monoclinic sulfur and decahydrated sodium sulfate are some examples of these types of crystal system. Let's discuss the last one, that is triclinic crystal system. Here the only possible lattice is primitive. As you can see, three axes are unequal in length and all angles are different. That is A not equal to B not equal to C and alpha not equal to beta not equal to gamma not equal to 90 degree. Potassium dichromate, boric acid, pentahydrated copper sulfate are some examples of these crystal system. Now you must have an idea about the crystal system, right? Friends, next we will determine the number of atoms in a unit cell. We know that any crystal is made up of infinite number of unit cells and each lattice point is occupied by one constant particle. That may be an atom, molecule or ion. Let us now consider what portion of each particle belongs to a particular unit cell. Consider three types of unit cells and for simplicity assume that the constant particle is an atom. Now let us start from the simple or primitive cubic unit cell. As you can see, in a primitive unit cell, atoms are present at corners only. In a crystal lattice, every corner is shared by 8 adjacent unit cells. Therefore, only 1/8 of an atom or other constant particles belongs to a unit cell. Here you can see some small spheres. Each small sphere represents only the center of the particle occupying that position and not its actual size. Such structures are called open structures. Well, the arrangement of particles is easier to follow in open structures. Using this, we can understand the space-filling representation of unit cell with actual particle size. And this shows the actual portions of different atoms present in a cubic unit cell. Since there are 8 atoms present in a unit cell on every corner, then total number of atoms in one unit cell is equal to 8 into 1/8. That is 1. Thus we can say that there is only one atom present in the primitive cubic unit cell. Next one is body-centered cubic unit cell. In a body-centered cubic unit cell, there are 8 atoms present at each corner and 1 atom present at the center of the body. Therefore, the number of atoms present in a body-centered cubic unit cell is equal to 8 corners into 1/8 atoms per corner. That is equal to 8 into 1/8 is equal to 1 atom. And 1 body center atom is equal to 1 into 1, that is equal to 1 atom. Hence, the total number of atoms per unit cell in BCC unit cell is equal to 1 plus 1, that is equal to 2 atoms. So, the last one is face-centered cubic unit cell. In a face-centered cubic unit cell, there are 8 atoms present at each corner. As we all know, a cube has 6 faces. Therefore, a total of 6 atoms present at the center of each face. Well, here each atom present at corners is shared by adjacent 8 atoms and each atom present at the center of face is shared between adjacent 2 atoms. Therefore, number of atoms in FCC unit cell is equal to 8 corners into 1 by 8 atoms per corner. That is equal to 8 into 1 by 8. That is 1 atom. 6 face-centered atoms into 1 by 2 atoms per unit cell is equal to 6 into 1 by 2. That is 3 atoms. Hence, we can say that total number of atoms per unit cell in a FCC unit cell is equal to 1 plus 3 is equal to 4 atoms. Friends, have you heard of bravais lattices in your previous classes? No, but don't worry, I will tell you. A French mathematician, Bravais, showed that there are only 14 possible three-dimensional lattices and they are called bravais lattices. Now let's know the unit cells of 14 types of bravais lattices. Well, they are mainly classified into 7. So the first one is cubic lattices, and the unit cells of cubic lattices are primitive or simple, body centered and face centered. As you can see, here all sides are of same length and the angle between the faces are of 90 degree. So the second one is tetragonal lattices. Here the unit cells of tetragonal lattices are primitive and body centered. Well, here one side is different in length to the another and the two angles between the faces are of 90 degree. Moving to the third one, that is orthorhombic lattice. The unit cells of orthorhombic lattices are primitive, end-centered, body-centered and face-centered. Well, here all the sides are different, but their angles are of 90 degree. So the fourth one is monoclinic lattice. Here the unit cells of monoclinic lattices are primitive and end-centered. Here sides are unequal and the two faces have angles different to 90 degree. So moving to the fifth one, that is hexagonal lattice. Here two sides are equal in length. Also one angle on two faces are of 60 degree. So the sixth one is rhombohedral lattice. Here all sides are of equal length and also angles on two faces are less than 90 degree. So let's discuss the last one, that is triclinic lattice. Here all sides, that is small a, small b and small c are unequal and angles A, B and C are unequal. Also, none of them are equal to 90 degree. Okay friends, let's move on to the next topic, that is close packing in solids. What happens when substances form solids? Yes, they tend to pack together to form ordered arrays of atoms, ions or molecules. Then let's see how this order arises and what are the different kinds of arrangements possible. Have you ever noticed the arrangement of apples, oranges in a vendor's cart? Well, many times oranges and apples stacked nicely in a vendor's cart to catch your attention. It is a practical application of close packing. Then what about the honeycomb? Well, it is an excellent example of close packing in nature. Friends, do you know the constituent particles in solids are in the form of sphere? These spheres in the solids are arranged in different ways to leave minimum vacant space. These arrangement of spheres in different layers form the close packed structures. Solids are three-dimensional structures and we will develop their structure in steps. Well, let's assume these particles are spheres of identical size. Then first we will see the close packing in one dimension. There is only one way of arranging these spheres in one-dimensional structure. that is to arrange them in a row by touching each other. As you can see, in this arrangement, each sphere is in contact with two of its neighbors. The number of nearest neighbors of particle is called its coordination number. Thus, we can say that in a one-dimensional close-packed arrangement, the coordination number is 2. So, the second one is close packing in 2 dimensions. When a number of rows stacked up, a 2-dimensional crystal plane is generated. And this stacking can be done in 2 ways. So, the first one is AAA type. Here, as you can see, the second row may be placed in contact with the first one, such that the spheres of the second row are exactly above those of the first row. The spheres of the two are aligned horizontally as well as vertically. If we call the first row A type, then the arrangement of the successive rows are also of A type. Thus, the packing is obtained is called AAA type. In this arrangement, each sphere is in contact with 4 of its neighbors. Thus, the coordination number is 4. Then, what happens when we join the centers of these 4 spheres? As you can see, if the centers of the 4 immediate neighboring spheres are joined, a square is formed. Hence, this close packing is called square close packing in 2 dimensions. Moving to the next one, that is ABAB type. Here, the second row may be placed above the first one in a staggered manner such that its spheres fit in the depressions of first row. And the spheres of the third layer are placed in the depressions of the second row. If the arrangement of the first row is called A type and the one in the second row is different and may be called B type, and the arrangement of spheres in the third layer is again of A type and the fourth layer is of B type and so on, the packing thus obtained is of ABAB type. You can also see that each sphere is in contact with 6 of its neighbors, 2 on either sides, 2 in the layer below and 2 in the layer above. Therefore, the coordination number is 6. Also, if the centers of these 6 neighboring spheres are joined, a hexagon is formed. Thus, it is also called hexagonal close packing. If you compare both 2-dimensional close packing, hexagonal close packing has less free space and it is more efficient than square close packing. Well, as you can see, some vacant spaces are left after the close packing of the spheres. These vacant spaces are called voids or interstitial sites. Here, in this figure, the empty spaces are seen as curved triangular spaces. And these spaces between the spheres can be divided into 2 kinds, that is X and Y. The spaces marked X are the ones in which the apex of the triangles are pointing downwards, while the spaces marked Y are the ones in which the apex of the triangles are pointing upwards.